MEMS Oral Team Video Project. We are from MEMS 13. My name is Gautam. Another two members is Rafiq and also Irfan. Our MEMS device is MEMS Thermal Actuator. Now I am going to present the MEMS Thermal Actuator principle of operation. So the principle of thermal actuator is based on the coefficient of thermal expansion. A bias-mode actuator based on MEMS is made up of two materials with distinct thermal expansion coefficient. When the temperature is raised, both layers expand with their respective coefficient of thermal expansion, causing strain in both layers and causing resistor to bend to minimize the strain mismatch. So as we can see here, the input is temperature and the output could be the thermal strain or also the total deformation. This is the diagram of the bias-mode actuator, and as we can see in the thermal equation here, theta is the initial tilt or the bending is depending on the curvature coefficient and also the thermal expansion coefficient. And then for the sensitivity equation, we can see that it is depending on the tip displacement and also the change of the temperature. Now I'm going to present the MEMS fabrication simulation using the MEMS Pro. So this is the layout. The layout is actually the mask used when etching process is done. So we can see there is a 4 box representing the 4 sides here, and also we use the shape of polygon for this T2T shape. And then for the material database, there are 4 material used. So we had insert these 4 material properties inside the MEMS Pro. This is the example where we insert the material properties for the silicon substrate. Next, I'm going to present the MEMS fabrication simulation in the MEMS Pro. So these 4 colors are representing the respective material. So first, the substrate wafer. Then we deposit copper on top of the silicon. Then on top of this material, we deposit silicon dioxide and also deposit aluminium. And then for the process, we define that the mask layout just now as a mask. Then we do the etching. That's why we got this pattern. We etch the aluminium, then we etch the silicon dioxide, and lastly we etch the sacrificial layer, which is the copper. That's why we can see that here got gap. The gap is because we etch completely the copper. This is the final 3D model, and this is for the final cross section.
Assalamualaikum, my name is Muhammad Ifan Bisaluddin. I'm going to explain about ANSYS system. We have 3 parts, A, B, and C. So B, we have the input, steady state thermal that consists of temperature. C, we have the output, static structural aluminium that consists of total deformation and thermal strain. For A, we choose the wrong input. Then we import the material database. For the geometry, we import the MEMS Pro but fail as the IGS file. Then we sketch ourselves using design modular. So this is the geometry design modular. So for the A, we only have 2 that's successful. Then for the model, the green tick is successful without any error. So steady state thermal as the input temperature, static structural as the output, the thermal strain. So this is a mesh. For the temperature, we have 250 degrees Celsius. So this is the boundary condition. We have A as the feed support, B as the elastic support.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Rafiq Muhammad from RK86. From RK86, I'm going to present the ANSYS solution results. This is the structure for thermal stress. As you can see on the figure, there is a little bending on the structure. Alright, for the first graph here, this is the temperature versus thermal stress for 3 different material. We insert the same output here, which is temperature for the 3 material. We observe the thermal stress. The 3 material has different value of thermal stress, as they have different temperature expansion coefficient. The second graph here, this is a total deformation versus temperature. As the total deformation increase, and so does the temperature. And the third graph here is aluminium against the momentum. The same of the second graph, where aluminium increase, so that's the momentum of the structure here. That's all. Thank you.
Okay, let's continue. So for the MEMS thermal actuator for campus sustainability, first Sun energy is primarily an underutilized renewable energy source that has tremendous potential in countries with high solar irradiation, such as Malaysia, to meet low temperature industrial heat demands. Malaysia is located near the equator with the average monthly sun radiation of 400 to 600. It has a positive future as a location for massive solar energy projects. The Malaysian government is eager to promote solar energy being one of the nation's main energy source, and in UNIMED campus, a lot of electricity are being used.
Affordable and clean energy are included in the UN Sustainable Development Goals, with positive indicators that energy is becoming more sustainable energy and broadly available. The world is undergoing a development toward Goal 7 in underdeveloped nations. Access to power has begun to increase. Clean energy is improving, and renewable energy is making significant progress in the power industry. Solar system is proposed or used is by utilizing a MEMS thermal actuator. This solar technology can continuously produce clean energy for the campus while also being affordable, as guaranteed the return of investment ROI. While thermal actuator are in the solar energy cell or solar cell, the exposure of solar radiation raises the actuator temperature. According to degree of temperature, the actuator controls the angle of inclination with which the collector moves to face the sun. That's all. Thank you.